So prior to starting her second PhD at the University of Alberta, Dr. Mona Amadi Rad worked as an assistant professor of industrial engineering. Currently, she is conducting research on human factors in automation, which is an interdisciplinary examination intersecting engineering, management, safety science, computer science, and human factors. More specifically, she is examining human risks associated with the deployment of the enhanced train control system in the Canadian railways. Join me in welcoming Mona.
Hello, everyone. Can you hear me?
Yeah, sounds good.
Today, I'm going to present a literature review on cognitive impacts of cab warning systems and train control technologies. This literature was commissioned by Transport Canada and conducted as a part of my PhD research program. Increasingly, control systems are being automated in industries to improve safety and optimize operations. A current example is the enhanced train control system, which is being developed for the Canadian railways. Experience in various industries, for example, aviation and nuclear industries, showed that such technologies may cause unexpected impacts on human performance and introduce new sources of human risks. In some, these systems can both reduce and introduce human failure events. Statistics illustrate that human factors account for over 75% of major railway accidents, aviation accidents, and marine accidents. When it comes to nuclear plants failures, this number reaches to over 90%. Therefore, to get a better understanding of in-cab warning and train control technologies, characterize potential cognitive impacts, and allow for the creation of mitigation strategies, we reviewed the relevant publications and summarized our main findings associated with using diverse train cab warning systems. Through this review, we found that the prevention of signal pass at danger, overspeed, collisions, and train operators' vigilance are the primary focus of in-cab warning systems. Visible and audible signals are the two common types of driver-system interactions in train cabs. In total, first, visual warnings are activated to inform the train operator of a hazardous situation. If the train operator doesn't react to them, then an auditory warning is activated to accompany the visual alarm. After that, more visual signals are initiated to provide the train operator with relevant and advisory information. We also found that train cab systems can be categorized into three generations. The first generation, they only alert the train operator of an upcoming hazardous condition. They need no train operator acknowledgement and have no automatic brake intervention. Second generation, the train operator must acknowledge the warning, usually by pressing an acknowledgement button. If the train operator fails to do so, the emergency brake will be applied to bring the train to stop. And in the third generation, the train speed is continuously checked with the dynamic speed profile, and warning, system brakes, and emergency brakes are activated whenever needed. Emergency brakes are triggered in the situation when the train operator takes no action after the warnings and the brake curb speed is violated. We acquired such knowledge through reviewing cab signal device, such as automatic warning system in the UK, automatic train control technologies, such as PTC in the US and ETCS in the European countries, train-to-train anti-collision systems, train operator reminder devices, and train operators vigilance devices. Our main findings is main human factors issues associated with the introduction and use of in-cab running systems and automated train control technologies are workload complacency and over-reliance, loss of situation awareness, mode confusion, distraction, visual attention allocation, automatic responding, and memory failures. Most negative cognitive impacts of the system on train operators are a result of workload. An underload of the train operator resulting in boredom, fatigue, overconfidence, and complacency. And an overload resulting in irrational reactions, confusion, exhaustion, and over-reliance. In summary, the effect of automation on workload is mixed, and automation may increase or decrease the workload level. The reliability of a system can also play a key role in train operators' performance and can cause excessive trust and complacency. On the one hand, the greater the reliability of an automated system, the better the performance when the system is perfectly operating. On the other hand, the reliable automated system increases the tendency to get complacent, which makes the operator less vigilant and less capable of reacting to system errors or failures. We also found that the ability of a train operator to handle and cope with alarms differs between persons, for example, affected by their experience, route knowledge, and mental state, and situations. As an example, expected versus unexpected situations. We obtained these findings by reviewing 46 publications related to human factors and train control technologies. The distribution of the published papers and reports between 2002 and 2020 illustrates that the year 2017 is the most significant period for this research topic. Detailed analysis discloses that the UK and the US are the leading countries in research on human factors issues of railway automation, with an aggregate share of 65%. As you can see, about 40% of the publicly available studies in the field of research are reports published in non-scientific index databases. These studies were usually performed or at least sponsored by governments and regulatory bodies. The existing literature shows us that the real-world data, simulator test data, and expert judgment data are the main sources of information for human factors evaluation. 33% of the researchers used multiple data sources to get a better understanding of the ironies of rail automation. We also analyzed 13 automation-related accidents occurred in the railway industry, including 4 accidents in the US, 4 in the UK, and 1 in Iran, China, Australia, Singapore, and Korea, which confirmed that automated system failures, complacency of train operators, inconsistency of alarm performance with user expectations, and poor alarm design and management are common issues in human-automation interaction. According to our literature review and findings, we recommend that both the train operator and the context in which warnings are issued need to be addressed through alarm management and system design to ensure the intended response by the train operator. Enforcement-based train control systems can improve safety much further than the advisory-based systems as we had in first generation. However, due to the potential for negative cognitive impacts, automated braking of the system should be a result of the emergence of an unsafe situation, not reliant on a failure of the train operator to acknowledge. Human reliability analysis and human-in-the-loop processes are required to identify and reduce human-induced risks and improve the system performance. We aim to identify the impacts of train control systems on performance of train operators, determine potential human failure modes and their contributing factors, and formulate strategies to prevent or mitigate the negative impacts associated with the design and usability of ETC system on the Canadian train operators. To achieve these goals, getting full or partial access to any data such as railway incident and accident data, on-train monitoring and recordings data, simulator data, human factors evaluation data can be really useful for us. Thank you everyone for your attention, and I would like to acknowledge our sponsors, especially Transport Canada, for this research. Any questions?
Thank you so much, Mona, for that great presentation. If there's any questions, we do have a couple minutes, so we'll give it a second here and see if anyone throws something in the chat. All right, well, it seems like you might be off the hook. Well, thank you again for that great presentation.
Thank you.